Welcome to our today's webinar, PT, RTD or NTC, which is the best for your application. Choosing the right temperature sensors isn't always that easy, as so many parameters should be considered and compared. We are often asked about the major differences between PT, RTD and NTCs, or what are the essential advantages of PT, RTDs that contribute to longer life cycles and lifetimes to reduce costs. Let's learn from our experts about the sometimes subtle differences and advantages for your applications. Today, our speakers are Martin Bleifuß, who holds the position of Global Head of Application Engineering, and Bob Gliniecki, our Technical Solution Manager from the US, with a great background and knowledge in NTC and PT sensor technologies. Let's start the webinar.
Okay, thanks also from my side and a warm welcome. A warm welcome to our webinar. Looking forward to the next hour and the discussion with you. Start with the theoretical overview, and we then want to deep dive a bit in the applications, including the highlights, when and which technology brings an advantage to your application. As that theoretical overview, we want to compare the most commonly used technologies for temperature detections. In that situation, we want to compare the PTC and the NTC. The PTC is a positive temperature coefficient, the NTC is a negative temperature coefficient part working. That means both of these parts determine the temperature via a voltage drop, and they are passive components. PTs are built as a kind of a sandwich. Yeah, you can see that we start with an aluminium oxide. Let's try to use that pointer. We start with an aluminium oxide substrate. We put a very thin platinum thin film on that oxide. Then we use a structuring system to make out of that layer a meandration or meander form. And this design of the meander is connected with the pads to the outside world with some lead wires. Over the meander, over the thin layer, we put a glass layer as a protection. And after the connection to the outside world with the lead wires, we put more or less a connection or a fixation drop on top of that, to have isolation and also a better fixation of the lead wires. If we compare it to the NTC technology, it works in a bit different way. This NTC is less complex to manufacture. We have here that semiconductor bulk material, which is a composition of metal oxides in the most times, and the function is like a semiconductor. But the disadvantage is it's not so easy to calibrate. After that, you have two lead wires also to the outside connection, and the complete system is covered with a kind of a protective coating, mostly done with a dipping process. If it comes to designs, we have typical configurations, and the sizes are quite similar. That means if you have an NTC or PTC in front of you, the sizes are comparable. What we can see, here in that situation a lead wired PT element, and here you see a lead wired NTC. It's like a drop, as I said before, in a dipped design, and here we have a bit more rectangular design, which helps sometimes regarding functions and thermal coupling. We have also for sure SMD parts in use, both, that means NTC and PTC. We have some special designs like SOT and TO versions. And in the direct comparison, there are diode packages for NTCs available. If we jump now a bit more deeper in that theoretical part, we see more or less the here are the characteristics. Here's the characteristics in blue of an NTC and in orange for that PT element. A PT element here is an RTD with a positive linear characteristics. You see that very clear. If the temperature is increasing, the resistance is also increasing on the both axes. Resistance here, temperature here. Increasing temperature, increasing resistance. If you compare that to the NTC with what the blue curve shows us, you see that the NTC works like a semiconductor more or less, and it's a quasi-insulator. At low temperatures, the electrical conductivity is completely different compared at high temperatures. That means in the low temperature area, it's more or less an insulation or insulator, and in the high temperature range is more or less like a good lighter, a good semiconductor then, yeah. If you look on the nominal resistances, there's a big difference. If a PT will be described or is described, then we speak about R0. That means our ohmic value is named at 0 degrees. And in comparison to an NTC, the NTC is described at 25 degrees, more or less the room temperature. If it comes to the typical ohmic values which are available, a lot of NTCs have an ohmic value of 2252, especially in medical applications, and very, very common are 10 kilo ohms and 100 kilo ohms and higher also. The most NTCs have operating temperature starting at minus 50, minus 100 degrees, up to 100 or 150. Some special ones have also the chance to work up to 300 degrees, and there are really very special versions of that NTCs which are able to survive up to temperatures to 750 degrees. In comparison to our PT element, we are able to work from minus 196, let's say 200, up to 1000 degrees, which is quite a big range compared to the NTC world. Big advantage for the PT is, in general, that this curve is standardized. This is standardized in the DIN and the IEC. And if you have different manufacturers, then you will see they follow all that standards, and you can exchange manufacturer A to manufacturer B or manufacturer 1 to manufacturer 2 or 3 directly, because they are all fixed in that characteristics and written down in the norms. Yeah. If it comes to an NTC, you see that different manufacturers use different characteristics, and they are not really fixed in a norm. That means it's not so easy to exchange, out of which reason ever, NTC 1 to an NTC 3. That means if there is a problem with the manufacturing side, or some company decided sometimes to stop production, then it's not so easy to find a suitable replacement for an NTC solution. It's possible, it's not out of scope, but it's a hard way to find that. Let's talk a bit about applications. We want to speak about different applications like body temperature monitoring, e-motor, heat metering, and industrial closing iron applications, and in the end about exhaust gas treatment. And we will take a look at these applications in a smaller deep dive, and therefore I will hand over to Bob for the first application.
Thanks, Martin, and welcome everybody. Thanks for joining us. This application is patient monitoring, basically human patient monitoring. And what you see in that picture is a monitor that is used to measure the temperature of infants when they were born. If you've ever seen a newborn, they lay in this warming table that looks like a sophisticated French fry warmer that keeps their body temperature stable. And this is a very common application. And it really is a good example of an ideal application for NTC thermistors. It has a narrow temperature range. In this particular case, 32 to 42 degrees C approximately. Very small sensor footprint, which is really important because you want to minimize discomfort to the patient. And you also want to have a fast response time. And in the case of an infant, you don't want to be intrusive. You know, they're small. You want a small device on them. Long lead lengths. These sensors tend to have long lead lengths, and since NTCs have relatively high resistance, the lead length is not a factor as far as calibration. Again, the NTC changes a large amount over a small temperature range, so resolution and precision temperature measurement is possible. And again, what's also essential is, in this type of application, is interchangeability. The manufacturers of the device make the sensors, and they need every sensor to be the same. And also, there are also aftermarket companies that make these sensors. So they have standardized on a particular curve for a particular piece of equipment. Again, as I mentioned, fast response time is very essential, and the small size, relatively small size, provides that advantage. And this provides an illustration of one of the advantages and one of the challenges of an NTC. You can see over a very, very narrow range, the resistance changes quite a bit. The resistance changes from about, I guess it's about 7,400 ohms to a little under 5,000 ohms over a 10-degree span. But the other issue is, though, even over that span, the alpha, the linearity changes. Mark, could you advance one slide, please? I think there's, there we go. So even over that small temperature range, from 32 to 33 degrees C, the resistance changes 300 ohms approximately. And from 41 to 42, it changes 191 ohms. Again, a large change, which is an advantage for this application because it gives you superior resolution, but also, again, nonlinearity. And it's not as much of a factor in a small temperature range like this, but over a very large range, it can be an issue. You can see on the curve that the curve gets very flat as you get to higher temperatures. Again, that large change allows some very tight tolerances over narrow temperature ranges, as tight as plus or minus 0.05 degrees C at 37 degrees Celsius.
Okay, in the next application, you can see an e-motor, which becomes more and more popular, especially with the electrification of the automotive world. That means in that typically application of the PT sensor, we can see and show the advantages. That means temperature control protects the e-motor from overheating and pushes the motor's performance limits. That's clear in our eyes, but it's not clear for some of our customers. That means if you drive with your e-motor, maybe on the Autobahn left lane, full throttle, and in that situation, the windings in that e-motor will increase the temperature. And there is a point where the insulation of the single windings will be destroyed. And if you will drive fast with your e-mobility car, or if you have the special situation that you start driving from zero to a different or to a high speed, then the e-motor will heat up very quick, and you have to protect the e-motor for that heating effect. And therefore, a very good sensor should be installed. That means we need, in that situation, the wide temperature range, because in winter times, you start driving with your car sometimes at minus temperatures, depending on the area where you live in. But minus 20, minus 30 is even possible in the middle of Europe, and up to 250, which is the typical limit of a lot of insulation materials in that windings, is completely normal. That means we have to protect the temperature or the e-motor in a temperature range from minus 50 up to 250 degrees. And during the lifetime, this e-motor sees a lot of stress because of temperature cycling. That means if you start in these minus temperatures in the early morning, if you want to drive to your work or something like that, it starts at very, very cold temperatures or in very cold status, and then you drive directly, the e-motor starts heating up, and it's very, very stressful for all the materials inside to survive that stress. Even for a sensor, it's hard to survive, and this is the reason why that temperature cycling is so stressful. Because you do that more than one time per day. Typically, you do that a lot of times, depending the use case, how you use your car. But in the end, there are a lot of limitations and things you have to take care. If you look at the high current and voltages in the e-motor itself, you have to protect the sensor which is in use, and this is not so easy to overcome. That means we need a very precise temperature measurement, because you want to drive as long as possible on the left lane on the Autobahn. That means you want to go close to the material limitations in the e-motor. You need a reliable temperature control, because you want to have the same protection after after 5 years, because you don't want to reduce the speed because of a worse protection in that situation. And you need for sure a fast response time, which is only possible with an optimized sensor and an optimized position in the e-motor of that sensor. And the combination of that helps us to reduce that high stress temperature cycling, or to survive with our sensor and to protect the e-motor in the best way. Because of these challenges, we come to the more or less the requirements of these sensors after the use case, more or less. And then you can see directly it's important to have results after a temperature cycle test, because we see that this is the most stressful test you can have for that. And out of that reason, we made some tests before and after special temperature steps. We started 0 degree, 100 degree, 150 degree, 175 and 210 degrees. The most of our customers make at the moment the limit at 200 degrees, but we are also able to work up to 250 degrees. But then the most of the insulation materials of the windings will fail. This is the reason why we made these temperature steps. And what we make here, we heat up the system from minus 50 up to 150. We have a dwell time of 300 seconds in both directions. That means at the cold side is at minus 50, and also on the warm side at 300 degrees. And then we had it's a discussion, how many cycles do you want to have? We decided to do 1,000 cycles, and we made it in a powered version. That means the sensor was really connected to the outside world, and we measured out what's happened there. And then we do the analysis also after the test. We had 2 sensors in mind which we compare for that. or for that comparison, it's the EC3032. You can find that sensor type or that sensor assembly on our website. And inside that sensor assembly, it's a PT1000 M222 with an accuracy of f0.3. And we compare that with an NTC motor sensor out of the market. This was not a fiction or something like that. We bought that on the market for exactly that application. And the result is like shown here. To explain a bit the graphics, we have to say what we try to show here. We have on the left side our EC3032 results, and here the results of the NTC. We see with these lines in orange the tolerances from our sensor, and we see the tolerances from the NTC. And this is what the manufacturer highlighted on the data sheet. You can see also that these limitations are quite far away from the real life. Maybe there are some deviations during their processes that they want to have this very open or wide window, but we are compared very narrow in the situation. And what you see here, you see yellow and green dots, and the yellow dots are before the measurement and before the test, before the stress, and the green ones are after the stress. And you see that our measurement results are quite similar before and after the stress. And here you see a bit more deviation before and after stress. In general, we made that after 150 degrees stressing, and here we see the results after 210 degrees stress, and the result is quite obvious. That means the PT version, it's the EC3032, is quite stable. We also say we need higher tolerances at higher temperatures, but as you can see directly on the results, they are really comparable to the 150 degree step. If you compare it now to that version of the NTC result, it looks a bit different. Yeah, what we can see, you see that the accuracy and the consistency of the NTC is a bit worse, or compared to an PT, it's not so good. If it's good enough, it's good, yes, but if it's needed to reduce, for example, a safety margin, I think it's a good idea to work with an EC3032 or with a PT element in general. Yeah, that means in this application, that could mean that the manufacturer needs to install a bigger safety margin and would therefore decrease the performance limits of the e-motor. If not, he would even risk to harm the motor components. That means if you stay with the same safety margins and the performance of the sensor is getting worse over the time, you risk a bit the isolation, you risk the performance of the e-motor, and this is unfortunately not repairable. That means, a burnt insulation is burnt. It's a problem, especially for e-motor, because it's one of the most expensive parts in an e-mobility construction. Okay, now I want to jump over to heat metering and overhand to Bob.
Thanks, Martin. If you've ever walked around New York City in the winter after a snowstorm or other cities, you may have noticed that a stripe of snow is melted on the sidewalk. That melt is caused by underground steam and hot water pipes. The power utilities provide centralized steam and hot water to heat buildings. This method of heating is used widely in many cities in Europe and also in China. The big difference is in the States, it is not billed per individual apartment or flat. It's billed to the building. In Europe and China, each individual flat must be billed for the use of heat. And the principle, it uses mass flow. This heat meter system has two temperature sensors. One's measuring temperature in, one is measuring temperature out. Combined with measuring the flow, you can calculate how much heat was actually used by that apartment. And again, for water, the range is approximately 0 to 40 degrees C. It's higher for steam. Again, this is used very widely. So millions of these parts are manufactured per year. So you have to have large-scale manufacturing to be able to manufacture a consistent part. Interchangeability is necessary because basically the product has to be backward compatible with systems that are already installed. You may need to install a new sensor to an old system, and it has to be compatible. Good long-term stability is essential for accurate measurement. And one reason why accurate measurement is critical is because basically people are being billed for their energy based upon this measurement. So it's a highly regulated application, again, because money's changing hands. No one wants to get cheated and paid too much. On the other hand, the supplier wants to get the fair price for the heat they're supplying. Again, fast response time is accurate. Fast response time is important for accurate and traceable measurements. Again, this is well-defined properties that are needed for this application to ensure accurate measurement and accurate billing. And while we're on the subject of response time, this graph illustrates the response time of a typical platinum element and a typical epoxy-coated chip thermistor. And the graph tells a story. You can see the response time of our platinum element in the, I guess that's orange, is much, much faster. And why is this critical? Many sensors are used for monitoring, but if you want to use a sensor as a safety device, it has to have a very fast response time. It has to respond quickly. Response time isn't fast. Whatever you're trying to protect can basically be destroyed or ruined before the temperature sensor reaches its full stable measurement. And again, you can see the platinum sensor has an extremely fast response time. Again, the other factor is packaging. So you want to take this sensor and package it accordingly. But again, you're starting with a sensor that already has a fast response time. So you have an advantage even before you put the sensor into a housing. And this is an illustration of our PCB sensor. This particular sensor was specifically designed for the heat meter application, but it has a lot of features on it that make it useful for other applications. The temperature range that it's capable of operating over is wider than the heat meter application. It can function from, as you see, from -40 to +150. The dimensions are very, very stable. And what does that mean? It means that each part is going to behave thermally the same from one to the other. Response time is going to be the same. And if you notice, there's a slight tip on the end, on the right side, that offsets it from the tip of the housing consistently. So again, the sensor will be located in the housing in every probe in the same place. You'll see that square wave pattern in the conductive path. That's a heat break. That provides thermal isolation that does two things. It shortens the response time. It also reduces what's called heat sink or stem effect. The cable you attach to this can influence the measurement of the sensor. And again, that helps prevent that. And it's really easy to make a probe with this. If you look at that diagram, the lower right-hand side of the slide, the green line is the sensor. The sensor width is matched to the inner diameter of the housing. So it's self-fixtures. You put it in, you don't have to worry about isolating it. And again, it really makes for fast assembly. You don't have to worry about insulating solder or weld splices with tubing. And again, if you look at the green sensor itself, on the left-hand side of it, that's a solder pad, and there's solder pads on either side. So you slide a jacketed cable on that, and you solder the conductor to both sides, and you're done. And it saves an incredible amount of assembly time, and it can be very cost effective for HVAC and other applications over that temperature range.
Okay. I think we come now to a complete different application for, as an example, industrial clothing iron application. That means everybody knows that from your home situation, and this PT RTD are increasingly used in that household applications, what you use at home to iron your suits and so on. Yeah, and for that reason, it's very, very important to have that special point of wide temperature range in, because compared to an NTC version, we saw that before in the graphs, that an NTC has a very good resolution on a very small area, but here we need a very good or a stable resolution over the complete range, which means in that situation plus 25 up to 300. Why is that so important? Yeah, you need that for that excellent ironing result. If you have different textiles, for example, the ironing performance and the result depends strong on the used temperature. And there are small temperature steps in between really essential for the result. If you have too low temperature, result is not fine. You have some knitters and yeah, not so nice and yeah, homogeneous flat surface as a result. And if you have a too high temperature, it's even worse, because you will destroy directly your material, your clothing in that situation. Yeah. What you also need, you need short heat up and reaction times. Why you need that? If you heat up and push your button, push your your steering wheel of that iron up to, I don't know, 170 degrees, it's helpful that there is a very accurate sensor in, that there is not an ranging that temperature. Otherwise you have that risk for destroying your material. Yeah, you need also that short reaction time. Nobody will wait till the sensor will show the real result. Everybody wants to work with that in a fast way, because ironing is not really a funny game. And most of us do that not as a hobby also. And out of that reason, we need in the end also a good drift behavior, because if you use that iron today, you will have the same result also in 5 years or in 2 years. Yeah, that means if you put 170 degrees on your wheel, you will have that 170 degrees. Otherwise, you risk your material, the textiles you will iron or you want to iron. And yeah, out of that reason, precise temperature measurement as the second point on the right side is, compared with the drift behavior, really, really important. And the reliable temperature control over the complete life cycle of that material, of that clothing iron is really mandatory. Yeah. That means this sensor is subjected to extreme temperature cycles, because you start more or less day by day at room temperature and go up to 300 degrees, depending what you do with that iron. And you need really a very precise and reliable temperature control over the complete time. This is the reason why it's so important to have that under control here. The good drift behavior is a very big point here, because it's easy to make an adjustment one time. It's also easy to keep that situation stable over some days, some weeks, but it's not so easy to have that stable drift behavior over years, which is mandatory, as I said before. And this leads us to a special test setup to test our equipment that it will fulfill the requirements of our customers, and we do it like before. We make an analysis at R0, R100, R300. That means we measure the resistance at 0, 100, and 300 degrees, and we do then a cycle shock test to stress the complete system and find out how stable and reliable our system in the end is. That means we warm the temperature system up to 300 degrees and cool it down to room temperature. We have a bit a slower dwell time than before, a lower dwell time than before because of the application here, and we have on the warm side 60 seconds and on the cold side 30 seconds. And we have also numbers of cycles with 1000 defined, and we made it also powered. And then we do the test again or the analyze again after this stress situation. And what we made, we compare our PT1000, again the M222 with the accuracy of f0.3, and compared it to 4 different similar international NTC types. That means we don't took something out of the box which nobody knows where it comes from. This is really a specified NTC with the temperature range by definition approved up to 300 degrees from leading NTC manufacturers. And in the end, we will get that, or we'll see that result. If you see the result at 0 degrees, there is not really a big deviation, not really. One is a bit worse than the others, but in general, I think with a drift with -1 Kelvin is quite fine, honestly spoken. If it comes to 100 degrees, it's a bit different. Yeah, you will lose a bit track with that one system, but in general, think about the application. You have to survive from from 25 degrees up to 300 a lot of times, and then you will see there is something happening. That means here you see in the orange graph our PT element, which is even after that stress quite stable with a lower than 0.5 Kelvin, and you see some other NTCs which have really a drift, what you can see here. Yeah, and this leads me to the situation. If it comes to an application over a big range and you have to take care about the drift, I think a PT version is quite good. Now we want to talk about a complete different application, exhaust gas monitoring, and for that I will overhand to Bob again.
Martin, I just want to thank you for sharing that about the irons. I can use all the precision control I can get when I iron. I've ruined many a shirt, and looking at your shirt and mine on the monitor, I think you did a better job ironing this morning than I did.
Okay, I can do a training for you.
That's our next webinar, ironing from Martin. Okay. Exhaust gas monitoring, otherwise known as EGT. This is one of the most stressful applications in temperature measurement, and specifically for platinum elements. A diesel exhaust and a gas exhaust has several points where the temperature is measured, and that the temperature can range cold start from -40 to +1000 degrees C. The change in temperature can be extremely rapid. It can change at a rate of more than 1000 degrees a second. You have a hot exhaust and you hit a puddle. The water splashes up on the exhaust pipe and instantly lowers the temperature. And all this is occurring under high shock and vibration. You're on a bumpy road, you're riding along, your exhaust is rattling, the engine's running normally hot temperature, and again, water splashes up. Very, very harsh conditions. Again, very key for this application, obviously, is robustness. It has to be simultaneously resistant to thermal shock, high temperature exposure, and mechanical shock and vibration. And the output has to be standardized. It has to be performed the same because you may need to replace the part, or if a manufacturer is manufacturing a platform of sensors for years, they need the same property without calibration for years. And again, on the road right now, we have over 100 million trucks with our sensors in it running and helping reduce the emissions in those vehicles. Again, long life. Some of these have been on the road for a decade or more. Long life is essential because we all know the cost of a repair, especially on a commercial vehicle. The cost of the repair is expensive, and getting that truck off the road is expensive, but especially now with the way logistics are, you need that truck on the road. So it's really important that the sensor is reliable. And this really shows how robust the sensor is. It has a very wide operating range. Again, like I mentioned previously, you get water splash, you get an instant drop in temperature. In this particular test, the sensors are inserted into a hot oven in temperatures excess of 900 degrees C, and they're left in there to dwell, and they're pulled out, and cool compressed air is blown on them. You can see the sensor tube is glowing red hot, and our sensor element is inside there and working just fine, measuring that temperature. And that test is repeated for thousands of cycles. And again, the sensor continues to perform. It will duplicate. It'll basically model a long use cycle. And again, our sensors pass this test. We have a sensor that can be used to 1,000 degrees C under these conditions, and again, and works with very high stability and high accuracy. Again, the sensor, years of design were put into the sensor. Basically, it was designed with manufacturing and techniques and materials that to ensure they were all compatible to withstand that very large change in temperature. And again, very, very harsh vibration conditions. And it's what we call, the test is what we call shake and bake. It's the test that the part is brought to high temperature under vibration. And again, since we designed the part specifically for these conditions, our parts meet or exceed the requirements of that test. This really illustrates the robustness and the accuracy of the sensor. That dotted line is the tolerance for the part. And again, the lines there are test samples for temperature cycling. And again, it's 5,000 cycles between ambient temperature and 1,000 degrees C with a 5-minute dwell at each phase and under power. And these tests under power are harsher because there's an electrochemical factor that's added when you have the part under power. Typically, results unpowered are better than under power. As you can see, the results are excellent, and the scatter is low. There's similar performance. There's no outliers. Again, this demonstrates the performance that our sensor will give at temperatures up to 1,000 degrees C. Again, this technology is applied to our other sensors that don't need to go to 1,000 degrees C. The core technology is the same, but special technology is used to stretch the limits to make a sensor to 1,000 degrees C.
Okay. At this position, or at this point of the presentation, you can say we have looked at 5 very, very different applications. That means we have healthcare, we have exhaust gas treatment. I think this is really, really a big range in applications. And we've shown the advantages and the disadvantages of each technology. Both NTCs and PT sensors have for sure reason to exist, and of course they just need to be used in the correct way. This is the core message. That means if you have an application, think about application range, think about robustness, think about resolution, and in the end you will find also a suitable sensor solution or sensor probe or a sensor configuration for your application. That means an NTC shows a price advantage for low temperature and small temperature ranges, and for low application demands, I will call it. Yeah, we hear quite often that NTCs in the market are cheaper when only looking at the component cost itself, but the advantage no longer exists when taking the total cost of ownerships into account. That means maintaining costs, costs of hardware, software, how do you take care about drift behaviors and things like that. That means if you work with high temperatures over a wide temperature range, on the other hand, applications subjected to many temperature cycles, high accuracy is needed, or you want to ensure that the sensor can be replaced without any restrictions from supplier A to supplier B, then I think a PT RTD will be the first choice. Please keep that in mind if you make your choice for your application in the end. Yeah, that means, there's, I think, room for all technologies, and you as a designer, you have to take care about the right choice.
Yeah, we can offer you further help. I mean, I'm here in the States out of our office in Pennsylvania, and Martin is the head of a great team in Germany of applications engineers that really do a great job, and we're prepared to help you. Maybe you have some questions, maybe you're not sure about a design, but we're really prepared to help you put together the design that's best for your application.
Mm-hmm. That's completely right, and I can only underline what Bob said. If you have special questions, please take directly in contact with us, and we will take care about it.